6.5 million kilometers. That is how far the James Webb Space Telescope is from Earth right now. That distance is so vast that if you tried to drive there in a car traveling at 100 kilometers per hour without stopping, it would take you more than 83,000 years to arrive. The light that the telescope collects from distant galaxies has been traveling through the universe for over 13 billion years. It left sources of light when the universe was less than 500 million years old. When that light finally reached the James Webb Telescope in the summer of 2022, it revealed something that transformed how astronomers understand the history of the cosmos. But the discovery that shocked scientists was not the ancient galaxies. The discovery was that those ancient galaxies should not exist at all. The James Webb Space Telescope cost approximately $10 billion to build. It took 30 years to develop. It was designed by tens of thousands of engineers and scientists across multiple countries and institutions. It was supposed to be the most powerful telescope ever built. It was supposed to see further back in time than any human instrument had ever seen. What nobody predicted was that it would immediately find galaxies that contradicted everything astronomers thought they understood about how galaxies form and evolve. This is the story of the first year of the James Webb Telescope, not the mythology of discovery, the shock of reality. The first image that James Webb captured was released on July 12, 2022. It was a photograph of a galaxy cluster called SMACS 0070. The image showed thousands of galaxies. Some were nearby. Some were so distant that their light had been traveling for 13.6 billion years. The image was beautiful. But the beauty masked something more significant. When astronomers analyzed the light from the most distant galaxies, they found something disturbing. The galaxies were larger than they should be. They had more stars than they should have. They appeared to be more mature than they should be. A galaxy that forms only a few 100 million years after the Big Bang should be small and chaotic. Instead, these galaxies appeared organized and massive. The implication was that either the models of galaxy formation were fundamentally wrong, or that the universe was behaving in ways that current theories could not explain. The technical challenge that the James Webb Telescope solved was enormous. To see light from objects that are 13 billion light-years away, you need an instrument that can collect incredibly small amounts of light and amplify them enough to be detected. The James Webb Telescope has a mirror made of beryllium coated with gold. Gold was chosen because it reflects infrared light exceptionally well and because it is inert, meaning it does not corrode or degrade. The mirror is segmented into 18 hexagonal sections. Each section can be adjusted independently using actuators that can move the segments with a precision of nanometers. 1 nanometer is 1/1000th of a meter. The precision required to keep those 18 segments aligned is equivalent to keeping the surface of a swimming pool smooth to within the thickness of a human hair from a distance of several kilometers. The telescope had to be launched folded, like an origami structure, because no rocket existed that could carry it in its fully deployed configuration. Launch took place on December 25, 2021. The telescope was folded inside the Ariane 5 rocket. Then it was launched toward a point in space called Lagrange Point 2. This is a location where the gravitational pulls of the Earth and the Sun balance perfectly. At this point, the telescope could maintain a stable orbit relative to Earth without using significant amounts of fuel. But reaching this point required flawless execution. The telescope had to unfold in space, the mirror segments had to deploy, the sun shield had to open. Any single failure would mean the loss of a $10 billion instrument and the scientific program that depended on it. The team at NASA and the Space Telescope Science Institute held their breath for 29 days while the James Webb Telescope unfolded itself in space. Each step had to work perfectly. If a single actuator failed to move a mirror segment, the entire instrument would be worthless. If the sun shield did not fully deploy, the telescope would overheat. If the deployment sequence had a single error, there was no way to repair it. Nobody had ever done this before. The most complex space deployment in human history was happening automatically, guided by software that had been tested endlessly but could never be perfectly predicted because space is not like Earth. Temperature extremes, radiation, vibration, any of these could cause something unexpected to happen. Everything worked. The James Webb Telescope reached Lagrange point 2. The mirror segments aligned themselves. The sun shield deployed. The telescope began to cool down to its operating temperature of approximately -233 degrees Celsius. And then it started seeing. The first targets were carefully chosen. Astronomers wanted to observe bright objects that were relatively nearby to verify that the telescope was working correctly before committing valuable observation time to more distant targets. The early observations confirmed that the telescope was functioning beyond specifications. The images were sharper than expected. The sensitivity was greater than predicted. And then came the discovery that would drive the next year of research. When James Webb observed the deepest regions of space, it found galaxies that had assembled themselves far faster than any model predicted. Galaxy formation requires gravity to pull together gas and dust into structures. This process takes time, billions of years in conventional models, but the James Webb Telescope was observing galaxies that appeared to be fully formed only a few 100 million years after the Big Bang. The light from these galaxies had been traveling for 13.2 billion years to reach Earth. When that light was emitted, the universe was less than 500 million years old. Galaxies at that age should be young and small and chaotic. Instead, they appeared mature. The team of astronomers who analyzed these observations faced a choice. Either the observations were wrong, which seemed impossible because the telescope was working perfectly, or the models of galaxy formation were incomplete or fundamentally incorrect. The weight of evidence suggested the models were wrong. But how could models developed over decades by thousands of scientists be that far off? The answer that emerged was that the models had been missing something crucial. The early universe may have contained more dark matter than anyone realized. Dark matter is invisible matter that exerts gravity but cannot be observed directly. If the early universe had much more dark matter than current models assumed, it would have been far easier for galaxies to form rapidly. This single discovery from James Webb meant that dozens of research programs would have to be revised. It meant that PhD dissertations based on the old models would have to be updated. It meant that the entire framework for understanding how galaxies form had to be questioned, and this happened in the first few months of operation. The second major discovery came when James Webb observed the atmospheres of exoplanets. These are planets orbiting other stars. When an exoplanet passes in front of its parent star, the light from the star passes through the planet's atmosphere. Different chemical elements in the atmosphere absorb different wavelengths of light. By analyzing which wavelengths are absorbed, astronomers can determine what chemicals are present in the atmosphere. James Webb found evidence of carbon dioxide, methane, and water vapor in the atmosphere of an exoplanet called K218-8b. This planet orbits a star approximately 120 light-years away. The discovery was revolutionary because it proved that the telescope could detect chemical signatures in distant planetary atmospheres. But the discovery was also troubling because the amount of methane detected was far higher than models predicted it should be. Either the models of how planetary atmospheres work are incomplete, or the planet has some unknown process generating methane in vast quantities. The third discovery involved what are called gravitational lenses. When a massive object like a galaxy or a cluster of galaxies passes between Earth and a more distant object, the gravity of the massive object bends the light from the distant object. This bending acts like a lens, magnifying the distant object. James Webb used gravitational lensing to observe incredibly distant galaxies that would have been far too faint to see directly. The telescope observed galaxies that existed when the universe was only 250 million years old. These observations showed that the early universe was filled with far more galaxies than anyone had predicted. The implication was that there are many more galaxies in the observable universe than current estimates. If there are more galaxies, there might be more stars. If there are more stars, the statistical likelihood of life arising elsewhere in the universe increases dramatically. The fourth discovery involved the earliest stars. James Webb observed what appears to be a star cluster that formed approximately 300 million years after the Big Bang. The oldest known star clusters before James Webb were thought to be approximately 100 million years older. This discovery pushes the timeline of star formation back further than anyone expected. It suggests that the early universe was far more active in creating stars than models predicted. The fifth discovery was perhaps the most philosophically disturbing. James Webb observed what appears to be a massive black hole in the center of a very distant galaxy. Black holes are objects so dense that gravity prevents even light from escaping. The theory of how black holes form requires them to start as stars and then collapse under their own gravity. But a supermassive black hole like the one James Webb observed would have required time to grow through multiple generations of star collapse. There should not be enough time in the early universe for a black hole this massive to exist, yet it does. This contradiction suggests that either black holes can form through mechanisms that are not yet understood, or that black holes existed in the early universe in abundance, which contradicts all current models of black hole formation. The sixth discovery involved organic molecules. James Webb detected complex organic molecules in the dust surrounding distant galaxies. These molecules are the building blocks of life. The detection was not entirely unexpected because complex organic molecules had been found in dust clouds within our own galaxy. But the abundance and diversity of these molecules in very distant galaxies was surprising. It suggested that the chemistry necessary for life may have been present throughout the observable universe almost from the beginning. The seventh discovery was about the expansion rate of the universe. Astronomers have long argued about exactly how fast the universe is expanding. Different measurement techniques give slightly different results. The discrepancy is small, but it is persistent. Some measurements suggest the universe is expanding faster than other measurements indicate. James Webb made new measurements of the brightness of distant supernovae, which are explosions of dying stars. These measurements provided new data for calculating the expansion rate. The results still showed a discrepancy between different measurement methods. The universe might be expanding faster than physics currently predicts. If this is true, it could mean that dark energy, the mysterious force accelerating the expansion of the universe, is far more powerful than anyone thought. The eighth discovery involved the composition of the early universe. James Webb observed that the early universe contained far higher abundances of heavy elements than anyone predicted. Heavy elements are created inside stars and released when stars die. In the current universe, galaxies in the early stages have very little heavy elements. But James Webb found galaxies with surprising amounts of heavy elements existing only a few 100 million years after the Big Bang. This suggests that the first generation of stars was far more massive and died far more rapidly than any model predicted. If the first stars were that massive and died that quickly, they would have seeded the universe with heavy elements at a rate far faster than expected. The ninth discovery was about dust in the early universe. Dust is everywhere in space. It blocks light. It absorbs energy. It is created when stars die and their materials scatter. James Webb detected enormous quantities of dust in very distant galaxies. The implication is that the first stars must have existed, lived their lives and died, creating dust, all in the first few 100 million years after the Big Bang. This timeline is far shorter than current models allow. Either the first stars were incredibly massive and short-lived, or they formed at a rate far higher than expected. The 10th discovery involved what are called gravitational waves. These are ripples in the fabric of space-time itself, created by extremely violent events. James Webb cannot detect gravitational waves directly, but when gravitational waves are produced, they often create observable light as well. James Webb observed the aftermath of colliding neutron stars. These are the remnants of massive stars that have collapsed into incredibly dense objects. When two neutron stars collide, they produce gravitational waves and they produce a burst of light. The observations from James Webb provided new data about how heavy elements are created in these collisions. The data suggests that neutron star collisions produce significantly more gold and other heavy elements than previous models predicted. As the first year of James Webb observations continued, a pattern emerged. Almost every observation revealed something that contradicted existing models. The universe appeared more complex, more active, and more abundant than any prediction. Galaxies formed too quickly. Black holes grew too fast. Elements were created too efficiently. Stars were born too rapidly. Every single discovery suggested that physicists did not understand the early universe nearly as well as they thought they did. By the end of the first year, the James Webb Telescope had fundamentally changed astronomy. The images from the deep field observations were released to the public, and they became the most viewed astronomical images in history. Millions of people saw images of galaxies that existed 13 billion years ago. They saw the universe as it was, when only 5% of the current age of the universe had passed. They saw galaxies that should not exist, and black holes that should not exist, and elements that should not exist in such quantities. The James Webb Telescope did not answer the big questions about the universe. Instead, it revealed that the big questions were far bigger than anyone had realized. The legacy of the James Webb Telescope is not that it confirmed what astronomers believed. The legacy is that it revealed how much astronomers did not know. The first year of observations will drive research for decades. The contradictions between observations and models will require entirely new theories. The universe, it turns out, is far stranger than anyone imagined when they decided to build a $10 billion telescope to look at it. What aspect of the James Webb discoveries fascinates you most? The ancient galaxies, the exoplanet atmospheres, the impossibly early black holes, the abundance of elements in the young universe? Tell me in the comments what you would like to explore deeper about these discoveries, and we will dive into the specific research that is challenging everything we thought we knew about how the cosmos works.